Excellent. This is actually, as a percentage, much larger than usual. How many of you have heard about Cassandra before? Okay, good. So we're going to preach to the choir a little bit. My name is Peter Halliday. I work at DataStax, and I'm on a team. I'm a senior software engineer that is on a team for Ops Center. We're going to get into what that is in a little bit. But what that means is it wasn't too long, actually, until I was where you are. I graduated with a master's degree in June of 2013 from Cornell University with a specialty in distributed systems. And I got hired at DataStax working on distributed systems, programming in Python, programming in Clojure, which is a functional-based language on the JVM. If you are interested in any of those kind of topics, you can certainly geek out with me after the talk. But we're going to learn a little bit about Cassandra, and we're going to, I've already asked the question about DataStax Cassandra, but some of you might not know that you are using Cassandra already, actually. How many of you guys have filed your taxes with TurboTax? Raise your hand. Okay. You've used Apache Cassandra. If you ever played Call of Duty, if you've played Call of Duty, you've used Apache Cassandra. Have you ever done something on Instagram or Spotify? What about Netflix? So as you can see, a theme of these is if you have a large amount of data, then you might want to consider Apache Cassandra. So what is Apache Cassandra? It's a massively scalable NoSQL database. NoSQL databases, a lot of people are starting to call it a post-relational database. This is unstructured data that, and usually it's stuff that you want to distribute all over the world. So it's big data, it's multiple data centers, you want no single point of failure, you want continuous availability without compromising performance. So we cut across a bunch, I mentioned a lot of different kinds of customers. Here are an example of a bunch of workloads that are customer segments that we have that utilize Cassandra. Anything from eBay using in e-commerce to fraud detection with Barracuda networks, to sensor data. I mentioned Call of Duty, online games, a lot of different kinds of data. This isn't just, online websites. They use Cassandra for a lot of very important reasons. One is they have data centers all over the world, and they have customers all over the world. They want this data replicated automatically. They want consistent linear scalability. They want to guard against failure. Failure is going to happen. And so they want something, plus they want a masterless architecture. No slam against, our friends at Microsoft and Oracle, but a lot of those relational technologies, including MongoDB, have a single point of failure in this master server. And you'll see, as I introduce the architecture of Cassandra, that we get around that. So a little history lesson. Whenever you talk about Cassandra, you really have to give a hat tip to the Google Big Table paper and the Amazon Dynamo paper. If you're into distributed systems or databases, those are two papers that are publicly available that you should read up on. There was an engineer at Facebook that read those papers and decided to program a database, Cassandra, for a use case of their messages, their inbox app at the time. And so they created Cassandra, and they open sourced it and gave it to the Apache Foundation. One of our co-founders, Jonathan Ellis, kind of discovered it right around that time, and he is currently serving as the chairman of the Apache Foundation project. This is an open source project. We took aspects of both of their, Amazon Dynamo and Google Bigtable, combined it into both. So we're going to talk a little bit about some of the terminology of Apache Cassandra, and then we're going to dive into a read and write case both on the cluster level and on the node level. So what is a Cassandra node? Cassandra node is just a server that's running Cassandra software. And it could be real or it could be virtual in some cloud instance somewhere. So a Cassandra cluster is a group of these nodes that are working together. A data center is obviously a group of clusters. They can actually be logical, like within racks of a data space. They could be physical all around the world, or they could be virtual, like in some cloud like Azure or EC2. So the Cassandra cluster allows you to take data and spread it all around the cluster. So we're going to talk a little bit about how that is partitioned. There's two partitioning strategies we're going to talk about. One is the random partitioning, which is the default and recommended strategy. This strategy takes a hash key and assigns that randomly, basically equally around the cluster. The other is an ordered partitioning, which allows you to sort it in an ordered way that you would define. This is, like many things you'll learn, this is configurable. All these choices are configurable. So in data partitioning, I talked a little bit about in the random partitioning that we take your data and you assign some sort of partition key. That partition key applies a hashing algorithm that by default we use a murmur3 partitioner, which takes the partition key and creates a hash out of it. So for example, a hash is just a way to take arbitrary amounts of data and come up with a fixed length, in this case a long value that it maps to. And each of those, so each of the nodes in the cluster are assigned a token, for example, that is a number that's assigned to them. And that hash algorithm means that it's assigned a bunch of numbers that it's responsible for, from the token value to one more than the token value of the previous node. So it's able to decide on which node that data is owned. So that's how data is partitioned in Cassandra. We get that from the Amazon Dynamo paper. The second part that we get from Amazon is the replication strategy. And one of the central parts to the replication strategy is what's called replication factor. Replication factor is how many copies of the data do you want to have. This is something that's also configurable. Replication factor of 1 obviously is just one copy of the data. We don't recommend that. You could have a replication factor of 2. We recommend 3. This is something that is controlled at the key space level. So each key space you can choose a different replication factor. There's two kinds of strategies. This will control which replicas in your cluster will get that data. We're going to talk about the simple strategy and the network topology strategy. Again, these are configurable. So in this example, the first node has a simple strategy. This cluster has a simple strategy, a replication factor of 2. And the first node is probably the owner of that. That's the one that has been assigned that token. And simple strategy means the next replica will be the one that will get the second copy. If you have a replication factor of 3, the one after that will get that third copy. So that's simple strategy. It's pretty simple. It's the default strategy. Another useful one is network topology. And if you have multiple data centers, which Cassandra is optimized for out of the box without doing anything, you can control the copies per data center. So you can say, if you have a data center in London, you have a data center in New York, you want to make sure you want to have 2 in one location, 3 in the other. And we'll show how that happens on the right level in a couple screens. But network topology isn't just useful if you have multiple data centers. Let's say you have a bunch of racks in the same data center, and one of the racks go down because you have a switch problem. This happens all the time in the real world. You can use network topology to make sure that the data is stored on separate racks, and that way your data can survive that kind of failure. So that you might be asking yourself, I can tell you are, actually, how does Cassandra know about racks? It's ESP. No, actually, it's this thing called the snitches. So snitches is a bunch of our code that basically informs, it tells on each other about the topology of your application. And there's several snitches that you can use. Again, this is configurable based on your application. If you're running in EC2, for example, there's a special EC2 snitch that we can use. For example, you can see the last one, EC2 multi-region snitch. This can be used to make sure that you have separate data in separate regions. So if one whole region goes down, it can survive that kind of region. So we don't just tell on each other, the nodes don't just tell on each other about the network topology. It uses gossip to inform the other nodes based on what other nodes are down. That information, which nodes are down and which nodes are up, is spread through gossip, along with other messages that are spread through gossip. So another sort of terminology is load balancing. And so, like I said, we have a masterless architecture. You can read and write from any node. So the strategy that the client uses to connect to the nodes are one of these three strategies. And this is something as a developer you get to choose. You can say that you want to use the round-robin strategy. And that means it's going to connect to a random server in either the local data center or the remote data center. In this case, it just so happened to use local. But if you have a remote, it might take a little bit longer for your connection. So we often advise to use the DC aware, the data center aware round robin. And what that does is it gives preference to the local data center, which will be faster. But if there's a failure, then it will automatically switch to the next data center so you can survive that kind of failure. And lastly, like I said, is token aware. Because we use, because the client knows the kind of partitioner that you're using, this hashing algorithm, we know what request you should, in the token aware strategy, we know which node you should be connected to. And this optimizes for faster connections. And this gives you more power as a developer to choose the strategy that best fits your application's use. So lastly, last part of terminology we're not going to get into a lot is virtual nodes. The strategy that I talked to about each node having a token, that's kind of an old legacy strategy. Virtual nodes expand that to allow you to assign multiple tokens per node. And so that means as you add nodes, you don't have to come up with these token values. And it also spreads the load out of adding a cluster around the cluster a little bit. Again, I'm not going to get deep into this. If you're interested in this, you can certainly talk to me after, or you can look at Planet Cassandra for details on this too. So let's get into reading and writing on a cluster level. Like I said, this is a location-independent event. So you don't have to worry about connecting to one particular master in this case. And writes are automatically partitioned, and they're automatically replicated for you. There's nothing that your application needs to do. So in writing data, the client sends a mutation to a random node. That node becomes the coordinator, like a quarterback, right? And that coordinator forwards all the updates to the replicas. In this case, it has a replication factor of 3, so automatically sends those. That coordinator may actually be one of the replicas, or it may not. In this case, it's not one of the replicas. So the replicas, whoa, overeager there. The coordinator forwards the updates to the replicas, and the replicas acknowledge that the data was written back to the coordinator, and the coordinator sends a successful response to the client. But that's not the real world, right? Like, accidents kind of happen. So when only 2 nodes respond, what should happen? Well, that's really up to you as a developer what should happen. And that's when I'm going to introduce something called write consistency. So you might have heard of a term called eventual consistency. At Apache Cassandra at DataStax, we prefer something called a tunable consistency. That as a developer, you get to choose how consistent do you want your data. Do you want to have strong consistency, or do you want weak consistency? This is something that is tunable by you per application, per read, per write, across multiple data center operations. We're going to talk about 4 consistency levels. One of them is any. So that means if you write, as long as it happens to one of the replicas, it works. That's any. Quorum is a majority across all the data centers. And local quorum is just that local data center. Just a quorum, and the quorum is defined as 51% or more. Or all. That's the strongest consistency. Very similar to, like, you know, more of a relational model. So an example is in the failed node from earlier. If you could save questions to the end, if that's okay. So in the failure example, will this successfully succeed if you have a quorum? Well, yeah, of course, because a quorum is a majority. Whereas if you have two failures, obviously that's not going to succeed, right? Because that's not a majority. As an aside, there's actually a solution to this because we have one. There's actually a configuration setting that allows settings, if you're using a DataStax driver specifically, this is easily configurable, to allow you to back off to another strategy so that if you're using local quorum or quorum, it will back off to any if you want it to. That's something that you can also choose and configure. So, because we're optimized for multiple data centers, if you have multiple data centers, the coordinator, after sending the copy to the replica, will send to a remote data center that node will become a coordinator and send to the replicas in that data center. And then the replicas will send the reply back to the client. So in the down node scenario, how does the node eventually learn of the data? The node learns of the data because the coordinator stores in memory a hint of the data for that node. And when the node comes back online, the data is replayed to the hint, is replayed to that node. And there's actually, we're going to talk about in the read path in just 2 slides or so, we're going to talk about another scenario in case that node doesn't get that data. So about reading data, it's very similar. A client connects to a random node. That node becomes the coordinator. And that coordinator sends the read request to the replicas. The replicas send the data back, and the data gets sent back to the client. So in the case of the failure I talked about in the right path, where one of them failed, so when the read comes in, that read might be stale, maybe because it didn't get that hint for some reason, right? In that case, how does you have duplicate nodes, how do you settle the dispute? The coordinator sees that one of the nodes have old data, and it sends the new data back to the client, and then issues a request to the out-of-date node to refresh their data from one of the other nodes. And so that's another method that we repair itself. There's also a percentage chance that this will happen randomly. There's a configuration option that will let you tune this. The percentage chance that a read repair will be done automatically. So the cluster is really designed to help repair itself. This is also a procedure that you can have done manually on the cluster. Obviously, there's some performance impact to this if you want to do this on a cluster-wide level. So you might be thinking to yourself, it's kind of inefficient, right? You have replication factor of 3 and a read consistency of 2. Why do you send 3 read requests out? Well, the answer is we don't really. We send 2 out automatically. And if those 2 don't come back quickly, then we send out an additional one. So this is called an eager retry method, and it's a rapid kind of read protocol. So that's the read and write on a cluster level. We're going to dive very quickly into what happens on the node level. And we're going to mention 3 data structures: a commit log, mem tables, and SS tables. And what happens is a write comes in, and first it's written to a log-based architecture for rapid writes called a commit log. And this allows, if the node gets destroyed and the data hasn't been written to disk, we can replay these commit logs and make sure the data isn't lost. And at the same time, it's written to these mem tables, which are in-memory versions of these SS tables. And when a mem table is filled up, then it's written to disk in a permanent fashion called an SS table. These SS tables are immutable and can't be changed. And the only way to change them is through what we call compaction. And so, as you can see, as data is moved around the cluster and becomes less relevant, we could have duplicate copies of data, or we can have data that's in the SS tables that cluster is no longer responsible for. So compaction, what it does is it creates new SS tables from the old SS tables and then deletes the old SS tables. So this is the way that nodes update these SS tables. So that's what happens on a write. And read is a little bit simpler. Depending on your application, the first thing we do is look in memory, look in these mem tables. If you have a high write application, these might actually still be in memory, and then it's very quick. Otherwise, we look at what's called a Bloom filter. I'm not going to get into what a Bloom filter is, but if you're a student, I definitely highly encourage you to look up on Wikipedia about a Bloom filter. But basically, it's a high probability index that allows you to tell with high probability whether something is in one of these SS tables or not, so you don't have to scan through all the SS tables. And so then we look in the Bloom filter, and if we still can't find it, there is a chance it's still in the SS tables, and then we do a seek, obviously, across the SS tables. So usually, if it's in the database, it's caught in the Bloom filter, and it's returned rather quickly. And so that's what that's the read path. So that's Apache Cassandra, and I'm going to talk very quickly about what makes DataStax different. DataStax is a company that supports Apache Cassandra, and what makes us different as a company, as opposed to companies like Mongo or Oracle or SQL Server, is a couple things. One is DataStax Enterprise, which is a certified production version of Apache Cassandra. This is something that we've tested internally, and it's run with customers, like I said, like eBay and Netflix, and it's what they use. It's used across a variety of use cases, not just narrow segments of the market. Is integrated OLTP, integrated analytics, integrated search. It has in-memory OLTP and analytics. It has strong data protection. It has management tools. We'll talk about several of those. We also support a lot of different languages and drivers. In many cases, our developers are the ones who are writing these drivers, some of which case like a Ruby and Node.js, which are very new, and Python are open source. You can use these currently for free. Other versions of these are available as a DataStax customer. And so one feature that you should use DataStax Enterprise for is security. We have like basic security as a part of Apache Cassandra. You can use username and passwords. You can use object permission management. So don't allow user Joe to do a delete on this table because he's a dumbass. Or you might have default client encryption between certain nodes. But if you're an enterprise customer, you want real enterprise security, which is things like external authentication, which allows you to connect to Kerberos or Active Directory or LDAP. You want data encryption for the data that's at rest, so that people don't look at your data in the SS tables unless it's encrypted. You want data auditing. Those are all features that are part of DataStax Enterprise. Another feature is OpsCenter. I told you I was going to talk about the product I'm responsible for. Like as a hacker, we all love our tools that are on the command line. But when you have clusters that are like thousands of nodes and hundreds of nodes, you often want a browser-based tool or something that you can do large-scale operations across the cluster. This OpsCenter also allows you to do backups of your cluster. Even with replication, like people can do dumb things like delete whole tables and delete whole key spaces. You want to be able to back up from events like that. OpsCenter allows you to do that. You also want to be able to do things like alerting. So when people have certain spikes or certain other things, you can be alerted of events like that. One of the common scenarios for using OpsCenter, we use this internally at DataStax, is what's called provisioning. So let's say you want to, in Amazon EC2, you want to create 10 nodes. You can click the Create New Cluster button and add in the IPs of the machines that you've already spun up, and add in either the connection or the SSL key. It will automatically install, automatically optimally configure these machines, and then suddenly you have a 10-node cluster. And alternatively, if you have EC2 credentials, you can just log into your EC2 credentials, and it will automatically do all of that for you. So that's OpsCenter. It's also free to use, and it's something that can be used with both DSE and Apache Cassandra. If you're using Apache Cassandra, it will actually have, it won't have all of the abilities of DSE. But one of the big uses that people use Apache DataStax Enterprise is integrated search. For that, we use a technology called Solar, and I'm not going to get into the search and the analytics in fine detail. If you have questions, please let me know. But one of the benefits of this is it allows you, instead of setting up a separate Solar instance, we optimally configure these integrated for textual, geospatial, faceting searches, in the cluster, the Cassandra cluster. And you can actually segregate these so that the search nodes are run in a separate data center, so that your application doesn't load down your Cassandra, your customer-facing Cassandra data. So search is one thing that your application might need. It also might need analytics if you're doing NoSQL, so that you don't use joins. You might have to use something like Hadoop, which is what we use for integrated batch analytics. And if you're using the integrated Hadoop, it's probably because you don't have your own Hadoop, or you want to avoid the single point of failure in Hadoop. There is the name server has a single point of failure, and also HDFS. If you haven't tried to configure HDFS, it's kind of a pain, and so maybe you want to avoid that by using our integrated approach. Again, it gives you the benefit of having a separate Hadoop cluster that is automatically replicated because the Cassandra replication. But if you're a big enterprise, you have your own Hadoop server, and you want to have your own Hadoop connect automatically. This is something that we call bring your own Hadoop. And lastly, it's kind of the new thing, which is Spark, real-time real-time analytics. And this is with DataStax Enterprise 4.5. And this allows you to do things in virtually real time. So this kind of offering we think is very compelling as opposed to our competitors, which have single points of failure and don't have linear scalability. When you look at the benchmarks, our performance outweighs those performance as well. And as developers, I want to say two things. One is, I encourage you to use us for the hackathon or for projects. You can go to planetcassandra.org. You can go to datastax.com, look at customer use cases, look at tutorials. And lastly, we have a booth upstairs. We are hiring, and we do have student internships. Please come up and give us your resume. Drop by and talk to us a little bit. I'm going to be up there for a little bit. If you have questions about Apache Cassandra, how to use it in your application,